see the screen? Can you see the screen?
Yes, ma'am.
Okay. At first we do something different on different definite integral. It can be defined as the limit of a sum. Suppose fx be a bounded single-valued continuous function defined in the interval ab. Let us have a look in the figure. This is the graph of the function y equal to fx. This is the graph of the function y equal to fx, and it is defined in the interval. Okay, it is shown beyond these intervals a and b. Anyway, this function fx is defined in the interval a up to b, or you just consider the interval a up to b. In this interval, the function is continuous. It is defined everywhere and it is continuous everywhere. Now, let us divide this interval into n equal subintervals. We divide this interval AB into n equal subintervals, each of length h. And we denote the points by a plus h, a plus 2h, a plus 3h, up to the last point should be a plus nh. And a plus nh should be equal to b, so that b minus a should be equal to nh and h equal to b minus a divided by n. Now we define this, we find this limiting value. Limit h tends to 0, h into fa plus h into f of a plus h into f of a plus 2h up to h into f of a plus n minus 1 into h. What does it mean? You see, each interval is of length h. So if this point is a, the next point should be a plus h. The next point should be a plus 2h. And what is the, if you complete this, okay, if you draw this ordinate, these ordinates, you see if h is very small, then it becomes a rectangle very small width, and here the width is h and the length is f of a, because this length is f of a and the width is h, and the next rectangle and the width is h. So the area of this of the first rectangle is h into f of a. The area of the second rectangle will be h into f of a plus h. Now, if this h is big one, then the rectangle will lie beyond this graph. May lie beyond this graph. But if h is very, very small, very small, then all these rectangles will lie within this curve and this x-axis. Okay, so if you take the sum of this, where h tends to 0, this sum actually gives you the area of the portion bounded by the curve y equal to fx, the two ordinates x equal to a, x equal to b, and the x-axis. Okay, if you use a summation sign here, h is common to each term, so h into sum over r equal to 0 to n minus 1. So here it should be f of a plus r into h. If you put r equal to 0, you will get the first term, r equal to 1, the second term, r equal to 2, the third term, and so on. And when r equal to n minus 1, you will get the last term. Now here we just put down the value of h. The value of h is b minus a divided by n. Okay, and here just put down the value of h. It is b minus a divided by n. So you see this sum is actually defined as the definite integral of fx. It is another definition of definite integral. It is the definite integral of fx with respect to x between the limits a and b. That is by this integral limit a to b fx dx. This is another definition. This is, yes, any question? This is another definition. The rule for evaluation is same. F of after integrating sub of x, then it will be phi of b minus phi of a. So, but the geometrical interpretation is this. This actually it gives the area of the region bounded by the curve y equal to fx, the two ordinates x equal to a, x equal to b, and the x-axis. Actually, I have explained it. Now some special type of series by definite integrals. This was the definition. This sum, the limiting value of this sum is defined as this integral. Now, if you put a equal to 0 and b equal to 1, what happens here? Let us see. If a equal to 0 and b equals to 1, then b minus a equal to nh gives you 1 equal to n into h. That means h should be 1 over n. So here it will be integral fx dx will be integral 0 to 1 fx dx. It will be in the left side, and in the right side it will be limit n tends to infinity, then 1 over n. 1 over n sum over r equal to 0 to n minus 1, and here f of this is 1, so just f of r by n. F of r by n. Now you see you can take the limits for this r as 1 up to n. Why? Let us go back to the sum. You see here we have taken the area like this. H into f of a. You can take it like this. The area of the first rectangle could be h into f of a plus h. The next rectangle can have the area h into f of a plus 2h. So the last rectangle will have the area h into f of a plus nh. So in that case, r should be equal to 1 up to n. So here you can write r equal to 1 up to n or r equal to 0 up to n minus 1. It doesn't matter. So here either r equal to 0 to n minus 1 or r equal to 1 up to n. Okay, we can use this definition of definite integral in some particular cases for finding the sum of an infinite series. Yes. The first math is here. Evaluate the following. Limit n tends to infinity 1 square by n cube plus 1 cube, 2 square by n cube plus 2 cube, up to n square by 2 n cube. Here n tends to infinity. So this is the nth term, n tends to infinity. Now here from the lower part we are taking n cube common. From the each term we are taking n cube common. So 1 over n cube can be put outside. Here it will be 1 square divided by 1 plus 1 by n whole cube. Here in the second term it will be 2 square by 1 plus 2 by n whole cube. And here it will be n square divided by, I'm sorry, it should be, okay, it's okay, n cube plus n cube. Yes, n cube plus n cube, that means 2n cube. Okay. It's perfectly all right. From the first n cube, we are taking n cube common, so it should be 1 plus n by n whole cube. Okay. Now, here, if we write here 1 over n, that means you are multiplying each term by 1 by n square. So the first term will be 1 by n whole square by this. Second term will be 2 by n whole square by 1 plus 2 by n whole cube. In the last term, it should be n by n whole square divided by 1 plus n by n whole cube. Now let us put it in summation sign. So 1 over n into sum over r equal to 1 up to n. So it should be r by n whole square divided by 1 plus r by n whole cube. Right. If you put r equal to 1, you will get the first term, r equal to 2 the second term, and r equal to n the nth term. And here n tends to infinity. So by the definition of this sum, you see, of the definite integral, you see this was the definition here. Sum over, sorry, in limit n tends to infinity, sum over r equal to 1 up to n, 1 by n, f of r by n. It is 0 to 1, integral 0 to 1 fx dx. So here we are getting the same thing, limit n tends to infinity, sum over r equal to 1 to n, 1 over n, and a function of r by n. And this whole thing is a function of r by n, this one, function of r by n. So if we can write it like this, integral 0 to 1 here for r by n x. So x squared divided by 1 plus x cube. So now you just do this integration in the proper way. You have to take a substitution, 1 plus x cube equal to say u. So you will get 3x squared dx equal to du. So x squared dx will be 1 over 3 du. And then after doing the integration, you will get this. So finally, the result is 1 over 3 ln of 2. So here you see we have found the sum of this infinite series by using the definition of definite integral. There is another math, limit n tends to infinity, n to the power half by n to the power 3 by 2. So in each term, in the upper side there is n to the power half, and in the lower side it was n to the power 3 by 2. Here it is n plus 3 whole to the power 3 by 2. Here it is n plus 6 whole to the power 3 by 2. So in the last term, in the nth term actually, it should be n plus 3 into n minus 1. Yes, because in the first term, if you put n equal to 1, 1 minus 1 is 0. So just n. And if you put n equal to 2 for the second term, 2 minus 1 is 1. So just 3. Yes. And in the third term, you have to put n equal to 3. So 3 minus 1 is 2. 3 into 2 is 6. Okay. So now here you see n to the power 3 by 2 minus, n to the power 3 by 2 minus half. It will be 1 over n. Similarly, if you take here n common, and if you take it outside the bracket, it will be n to the power 3 by 2. So ultimately there should be an n here. So it should be 1 by n into 1 plus 3 by n whole to the power 3 by 2. So in the next term, it should be 1 by n into 1 plus 6 by n whole to the power 3 by 2. And in the last term, it should be 1 by 1 plus 3 into n minus 1 by n whole to the power 3 by 2. Okay, so now we can put it in a summation sign. Here it is 3 into 1. Here it is 3 into 2. And we are taking 1 over n common. So 1 over n must be common there always. 1 over n into, here comes 1 plus 1 by 1 plus 3 1 by n whole to the power 3 by 2. Then 1 by 1 plus 3 into 2 by n whole to the power 3 by 2. So when we put it in summation sign, it should be r equal to 0 to n minus 1. Because when you put r equal to 0 here, it is 1 plus 3 r by n. If you put r equal to 0 here, you are getting the first term 1. So here r starts from 0. And when you put r equal to 1, this second term, r equal to 2, the third term, and so on. Now it goes to the definition of the definite integral. It should be integral 0 to 1, then 0 to 1 f of r by n. What was the definition?
Ma'am, can you please define why it is 1 and 0?
Sorry? Why it is 1? This is just a special case. If you take a equal to 0 and b equal to 1, then you get this thing. Then you get this definition actually. If you have a limiting value something like this, then you can replace it by this integral. That's all. But this one is the general definition. This sum, the limiting value of this sum is defined as integral a to b fx dx. And this is actually the special case. And we are using the special case when a equal to 0, b equal to 1. This is just a special case, nothing else. So here it is a function of r by n. So it will be integral 0 to 1, 1 over 1 plus 3x whole to the power 3 by 2. So you can directly integrate it. It should be 1 plus 3x whole to the power minus 3 by 2 plus 1 divided by minus 3 by 2 plus 1 and then again divided by 3. And then you use the limit. Then we use the limit and we get the result, which is 1/3. Here we have just one more math. It is already given as sum. Limit n tends to infinity, sum over r equal to 1 up to infinity. N by n plus r. Okay, at first we take n common from this factor and r n plus r. So it should be n into 1 r by n. So the upper n and the lower n, they are cancelling each other. In the upper part we have just 1, and here 1 plus r by n. Now again we are taking common n square under the square root. We are taking n square common. So here remains 2 into r by n, and here r square by n square. So we take this n square outside the square root. It should be 1/n, and we take it, yes, we can take it outside the summation sign also. Limit n tends to infinity, 1/n, sum over r equal to 1 to, no. Here it cannot be infinity. It should be r equal to 1 up to n. If it is r equal to 1 up to infinity, we don't need this limit. Okay. What was it in the definition? Let us go back. Yes, it was either r equal to 0 to n minus 1, or it is 1 up to n, and then n tends to infinity. I think there is a mistake here. It should be r equal to 1 up to n, right? It should be n here, not infinity. I'm sorry. It should be n here, r equal to 1 up to n, then n tends to infinity. So this is a mistake here from the first step. It should be r equal to 1 up to n. Anyway, here we are, we have, okay, this 1/n is taken outside, 1 plus r by n, and here it is square root of 2 into r by n plus r by n whole square. So it can be replaced by this integral 0 to 1 dx divided by 1 plus x into root over 2x plus x square, right? 2x plus x square, and this 2x plus x square can be written as 1 plus x whole square minus 1. Now we take a substitution. Suppose 1 plus x equal to sec theta, so dx should be sec theta tan theta d theta, and the limit when x equal to 0, theta should be 0. When x equal to 1, sec theta is 2. That means theta is 60 degree. Yes, 60 degrees. So pi by 3. So the limit of this integral should be 0 to pi by 3. In the upper side, sec theta tan theta d theta, and in the lower side, this should be sec theta and root over sec square theta minus 1. That means tan theta. So this sec theta tan theta both are cancelling. You just have 0 to pi by 3 d theta, which gives you theta with the limit 0 to pi by 3. That means pi by 3. So these are the maths, and there are more maths in your books of this type. So you can do this math by yourself. Okay, I am closing this file and I am taking another file, which will be a very new thing: beta function and gamma function. Just a minute. Okay, I hope you can see the screen. Beta function and gamma function, very, very important functions. So this is the definition of gamma function. This function is defined by the integral. This is the notation for gamma n. Gamma n, it is pronounced in this way, gamma n. Okay, this is equal to integral 0 infinity x to the power n minus 1 into e to the power minus x dx. So you see this is an improper integral. This is an improper integral because of this limit infinity. So 0 to infinity x to the power n minus 1 e to the power minus x dx. This is gamma n. Now at first we show that gamma n plus 1 equals to n into gamma n. So one thing here, n should be a positive number, a positive real number. It may be any fraction, it may be any decimal, but it must be greater than 0. It is always a positive number to define this gamma function. And we can easily show that gamma n plus 1 equal to n into gamma n. Okay, we start with this definition. Our gamma n was integral 0 to infinity x to the power n minus 1 e to the power minus x. So by definition, gamma n plus 1 should be equal to 0 to infinity x to the power n, just one less than this number. The power of x should be just one less than this number. Okay, so x to the power n into e to the power minus x dx. Okay, we perform this integration. We write t for this infinity and then take limit t tends to infinity. Then we apply the method of integration by parts. Here we are taking x to the power n as the first function and e to the power minus x as the second function. So limit t tends to infinity will be there in both the terms, and here x to the power n into minus e to the power minus x, okay, with the limit 0 to t. Then for the second term, there should be minus whole integration d dx of first function. That means n into x to the power n minus 1. We put this n outside, and integral of e to the power minus x, it gives you minus e to the power minus x. So 2 minus sign gives you plus sign, and we are getting this integral. T tends to infinity. Now let us try to find the limiting value of the first term. So if you put the limits here for x, the first term, the minus, let us keep this minus and outside the limit, t to the power n into e to the power minus t when t tends to infinity. And in our last class, yesterday, we have seen that the limiting value of this function, t to the power n e to the power minus t, is 0. Here I am showing it again. It is a different way. Here I am showing it in a different way, not using Hospital's rule. You just write down the expansion for e to the power t. 1 plus t squared by factorial 2 plus t cubed by factorial 3 up to infinity. In some term, it may be t to the power r, and this r may be greater than n. In a certain term, this power of t may be must be greater than n anyway, because this series is an infinite series and e is any positive number. So there must be a number here, r, which should be greater than n. Anyway, from the lower part, you are taking t to the power n common. So the first term should be 1 by t to the power n. The second term, 1 by t to the power n minus 1. The third term should be 1 by factorial 2 into t to the power n minus 2, and so on. And when r is greater than n, it should be, you are taking t to the power n common, so it should be t to the power n minus r minus n divided by factorial r. The next term should be t to the power r plus 1 minus n divided by factorial r plus 1. The next term should be t to the power r plus 2 minus n divided by r plus factorial r plus 2 up to infinity. Okay, and when you use these limits, t tends to infinity. T tends to infinity. All the terms will be 0 before the term t to the power r minus n, because here when t tends to infinity, this term should be infinity. So for this, we will get 1 by 0 plus 0 plus 0 up to certain term, and then we will get infinity plus infinity, etc. So ultimately 1 over infinity, which gives you 0. So this is another method of showing that this limiting value is 0. Anyway, now from the second term, we had this n into limit t tends to infinity 0 to t x to the power n minus 1 e to the power minus x. Just like from this integral 0 to infinity x to the power n e to the power minus x dx, you are getting n into this. So from again, if you apply the integration by parts, you will get in the next term, you will get n into n minus 1, n into n minus 1 into integration 0 to infinity x to the power n minus 2 e to the power x. Okay, which actually this gives you gamma n. This gives you gamma n. Okay, we don't need to show it. Anyway, n into this is nothing but gamma n, and the first term is 0. So ultimately what you are getting, gamma n plus 1 equals to n into gamma n. N into gamma n. This is an important relation. Gamma n plus 1 equal to n into gamma n. It is true for any positive number n, any positive real number n. Now we will show that if n is an integer, then gamma n plus 1 is nothing but factorial n. If n is an integer, of course positive, then gamma n plus 1 will be equal to n into gamma n. So using this property, gamma n should be equal to n minus 1 into gamma n minus 1. In the next term, next step, it should be n into n minus 1 into n minus 2 into n minus 2. So ultimately, you see all the factors are reducing by 1, n into n minus 1 into n minus 3, then n minus 4, then n minus 3, n minus 4, etc. up to 4 into 3 into 2 into 1 into gamma 1, 1 into gamma 1. Now we will show that the value of this gamma 1 is 1. How? You see, by the definition of gamma function, gamma 1 should be equal to integral 0 to infinity x to the power 1 minus 1, because n is 1. Now n 1 minus 1 is 0, so we are left with only e to the power minus x. Now you perform this integration, putting t in place of infinity and then taking limit t tends to infinity. Just perform this integration and then use the lower limit and upper limit. Finally, you are getting, yes, because minus 1 by e to the power t. When t tends to infinity, 1 by infinity, it is 0. So minus minus plus 1. So remember, gamma 1 equals to 1. Gamma 1 equals to 1. So if you put it here, ultimately you are getting gamma n plus 1 equal to this, which is nothing but factorial n. Gamma n plus 2 only when n is a positive integer, otherwise not. Only when n is a positive integer. Now we define beta function. Beta function, beta mn, because here two parameters are used, m and n. Beta mn, it is equal to integral into 1 minus x whole to the power n minus 1 dx. Here n are positive numbers, positive real numbers, m and n. Okay, now at first we will show that beta mn equals to beta nm. So if m and n are interchanged, the value will not be changed. So according to this definition of beta function, beta nm will be equal to 0 to 1 x to the power n minus 1 into 1 minus x whole to the power n minus 1. Now to show this equality, let us suppose that x equal to 1 minus z. Let us use this substitution, x equal to 1 minus z. So dx will be equal to minus dz. Now change the limit. When x equal to 0, z should be 1. And when x equal to 1, z should be 0. So the limit now becomes 1 up to 0 and dx equal to minus dz. So in place of x, we write 1 minus z. So here the power is n minus 1 and what will be 1 minus x? 1 minus x should be equal to z. So here comes z to the power m minus 1. Now, using the property of definite integral, let us adjust this minus sign with the limits. So, minus sign will be plus if the limits are interchanged, 0 to 1. Now, at first we write this factor z to the power m minus 1, then 1 minus z whole to the power n minus 1. Now, you know, if the limits are not changed, the variable may be changed. In place of z, you can write x. This was the first property of definite integral. So 0 to 1, x to the power m minus 1 into 1 minus x whole to the power n minus 1, which is nothing but beta mn. So we see that beta mn equals to beta nm. Now, very important relation in between beta function and gamma function. This relation is very, very important. Beta mn equals to gamma m into gamma n divided by gamma m plus n. So let us prove this relation. We start from the definition of gamma function. Gamma n equals to integral 0 to infinity x to the power n minus 1 into e to the power minus x dx. So at first we take a substitution. Suppose that is x equal to z into y. Here it is mentioned that z is a variable, but it is not a function of x and y. So, if the integration is with respect to x or with respect to y, z will act as a parameter, not a variable, because z is not a function of x and y. Okay, so for this relation x equal to z into y, when you take the differential, dx will be equal to z into dy, because here z is a parameter. It is not a function of x and y. So now, for x to the power n minus 1, we have to write z to the power n minus 1 into y to the power n minus 1. This integral is with respect to, at first it was with respect to x, now dx equal to z into dy. Z into dy, so z into dy, and here this z to the power n minus 1 can be taken outside, and again z to the power n minus 1 into z gives you z to the power n, which can be kept outside the integral because here the integration now is with respect to y. So here remains y to the power n minus 1 into e to the power minus zy dy. Okay, now let us multiply both sides. This is an equality. We multiply both sides by this. Z to the power m minus 1 into e to the power z. So in the left side, we will have gamma n into z to the power m minus 1 into e to the power z. And in the right side, z to the power, there was already an n, now m minus 1. So m plus n minus 1 into e to the power z. So this whole thing is a function of z, so no need to write it under the integration sign because you are multiplying this thing to this integral. Okay, now we integrate both sides between limits 0 to infinity, and it is with respect to z. Integrate both sides with respect to z between limits 0 and infinity. So in the left side, gamma n integral 0 to infinity z to the power m minus 1 e to the power minus z dz. And in the right side, integral 0 to infinity, then this whole thing lies under this integration sign. But since this is a function, after integration there will be no y, yes, so whole thing will be a function of z. Okay, now do you know it? If you have multiple integrals, more than one integral simultaneously, then we can change the order of the integration. We can change the order of integration, just like we can change the order of differentiation and integration. Okay, so here the first integral was with respect to y and the second integral was overall with respect to z. Now we perform the integration with respect to z at first. So we have to put all the things which contain z under this integral with respect to dz. with respect to z. So here we are performing the integration with respect to z at first. So what terms are remaining here under this integral with respect to z? Z to the power m plus n minus 1 into e to the power z, and there is another function here, e to the power minus zy, which contains z. So this should be taken under this integration. So there are two terms actually, e to the power minus z into e to the power minus zy, and you can combine them. It will be e to the power minus z minus zy. Now taking minus z common, it will be e to the power minus z into y plus 1 then dz. So we put this whole thing under this integral with respect to z and put a second bracket here, and outside this second bracket there remains y to the power n minus 1 dy, and the integration with respect to y is done secondly after performing the integration with respect to z. Here we have changed the order of integration. Okay, now we take a substitution here for this z into y plus 1. Z into y plus 1 equal to t. Here the integration was with respect to z. So here z is the variable and y is a parameter, because z is not a function of y. There is no relation in between z and y. So y acts as a parameter here. So when you take the differential, it will be y plus 1 into dz equal to dt. Now we put this, use these substitutions here in this integration. For z, the value of z is t divided by y plus 1. So in this integration within the second bracket, in the upper side, it should be t to the power m plus n minus 1 divided by y plus 1 whole to the power m plus n minus 1. Then into e to the power minus this z into y plus 1 is t. So e to the power minus t. And what is the value of dz? Dz is dt by y plus 1. So dt by y plus 1. Close the second bracket. Outside the second bracket, y to the power n minus 1 into dy. Now, this term, this factor is y plus 1 whole to the power m plus n minus 1, and this is y plus 1. So if you multiply them together, the power of y plus 1 should be m plus 1, and which is free from any t, so you can take it outside this integral. Under the integral with respect to t, there remains t to the power m plus n minus 1 into e to the power minus t dt. So according to the definition of gamma function, it is nothing but gamma m plus 1. M plus n, sorry, it is nothing but gamma m plus 1. So you can, this is a constant now, and we can take it outside this integral. So under the integral with respect to y, there remains y to the power n minus 1 divided by y plus 1 whole to the power m plus n. Okay, now to perform this integration, let us put 1 divided by y plus 1 equal to u. Okay, so y plus 1 should be equal to 1 over u. So y should be equal to 1 by u minus 1, which gives you 1 minus u divided by u. So dy from this relation, dy should be equal to minus 1 over u squared du. Right. Now change the limits. When y equal to 0, u should be equal to 1. And when y equal to infinity, u should be equal to 1 by infinity means 0. So now the limit is from 1 up to 0. And dy equals to minus 1 by u squared du. And 1 over y plus 1 is u. So for this 1 by u plus 1 whole to the power m plus 1, it should be u to the power m plus 1. Yes, u to the power m plus 1, integral 1 up to 0, gamma m plus 1, m plus n remains outside. And now let us put down the value of y here. That is the y to the power n minus 1. And the value of y is 1 minus u by u. So it will be 1 minus u whole to the power n minus 1 divided by u to the power n minus 1. And the value of dy is minus du by u square. Yes. So we adjust this minus sign with these limits. The limit will be now 0 to 1. So u to the power m plus 1 divided by u to the power n minus 1 plus 2, that means n plus 1. And here 1 minus u whole to the power n minus 1 du. Okay, now u to the power m plus 1 minus n minus 1. So ultimately it should be u to the power m minus 1. And according to the definition of beta function, you see, you just replace u by x. It is nothing but a beta mn. So in the left side, it was gamma n into gamma m. So the value of beta mn equals to gamma m into gamma n divided by gamma m plus 1. Very important relation. Now there is another expression for this beta function as integral of sine and cos. Combination of sine and cos. We have to show that beta mn equals to 2 into integral 0 to pi by 2 sine to the power 2m minus 1 theta into cos to the power 2n minus 1 theta d theta. Okay, we start with the definition of beta function. It is integral 0 to 1 x to the power m minus 1 into 1 minus x whole to the power n minus 1 dx. Let us take x equal to sine square theta. So dx should be equal to 2 sine theta cos theta d theta. And adjust the limits. When x equal to 0, theta should be 0. When x equal to 1, theta sine square theta is 1. So theta may be equal to plus pi by 2 or minus pi by 2. Here we are taking plus pi by 2, but the same relation can be proved if you take theta equal to minus pi by 2. No problem. Here we are taking theta equal to pi by 2. Okay, so now the integral becomes 2 into integral 0 to pi by 2 sine to the power. Okay, x equal to sine square theta. So the power of sine should be 2m minus 2. Yes. And here 1 minus sine square theta whole to the power n minus 1. And the value of dx is 2 sine theta cos theta d theta. 2 remains outside. Now we adjust the powers here. Sine to the power 2m minus 2 theta, and there is another sine theta. So the power now becomes 2m minus 1. And 1 minus cos square theta is 1 minus sine square theta is cos square theta. So the power of cos theta should be 2n minus 2, but there is another cos theta. Ultimately it is this. 2 into integral 0 to pi by 2 sine to the power 2m minus 1 theta cos to the power 2n minus 1 theta d theta. This was the thing to be proved. Okay. Now we can get another expression for this integral 0 to pi by 2 sine cos. Let us put 2m minus 1 equals to p and 2n minus 1 equals to q. So m equals to p plus 1 divided by 2 and n equals to q plus 1 divided by 2. So the left side beta mn becomes beta of p plus 1 by 2, q plus 1 by 2, and in the right side it is 2 into integral 0 to pi by 2 sine to the power p theta cos to the power q theta d theta. So the value of this integral 0 to pi by 2 sine to the power p theta cos to the power q theta d theta should be equal to half of beta p plus 1 by 2 q plus 1 by 2. And using the relation beta mn equals to gamma m into gamma n divided by gamma m plus 1. So in place of m, let us write p plus 1 by 2, and in place of n, let us write q plus 1 by 2. So you are getting this relation. Gamma p plus 1 by 2 into gamma q plus 1 by 2 divided by 2 into gamma p plus q plus 2 divided by 2. If you change p by m and q by n, we get this expression. Integral 0 to pi by 2 sine to the power m theta cos to the power m theta is this. Gamma m plus 1 by 2 into gamma n plus 1 by 2 divided by 2 into gamma m plus n plus 2 divided by. Very important result for evaluating this type of integration. Now another important relation, gamma half equals to root over pi. So we start from this relation, beta mn equals to gamma m into gamma n divided by gamma m plus n. We now put here gamma m equal to n equal to half. Okay, so it should be beta half half equal to gamma half into gamma half divided by gamma half plus half. Half plus half is 1. Gamma 1. Gamma 1 is 1, and in the upper side it becomes gamma half whole square. Okay, so gamma half whole square equal to beta of half and half. Now use this expression for beta mn. We have got it. Beta mn equals to this 2 into integral 0 to pi by 2 sine to the power 2m minus 1 theta cos to the power 2n minus 1 theta d theta. So here beta half should be equal to, you just put m equal to half. If you put m equal to half, it will be 2 into half means 1, 1 minus 1, 0. Here also n equals to half, 2 into half is 1, 1 minus 1, 0. So it becomes 0 to pi by 2 sine to the power 0 theta cos to the power 0 theta, that means just 1. So you are getting pi by 2. So there was a 2 here, 2 into pi by 2 means pi. So gamma half whole square equal to pi. That means gamma half should be equal to root over pi. Gamma half equal to root over pi. And we are not taking the negative sign because you know gamma of a number is a positive number. Gamma of something is a positive number. Okay, now we prove this one, integration 0 to infinity e to the power minus y to the power 1 over n dy. It is very easy. Just start from the definition of gamma function and use this substitution, x to the power n equal to y, which gives you n x to the power n minus 1 dx equal to dy. And what will be the value of x? X should be equal to y to the power 1 by n. So this x to the power n minus 1 dx can be replaced by dy by n. So 1 over n remains outside. There is no change in the limit. Yes, 0 to infinity, and the value of x becomes y to the power 1 over n. Okay, so you are getting this expression. This is a very important result for this improper integral, integration 0 to infinity e to the power minus x squared dx equal to half into root over pi. Very important result. We start from this gamma n and we substitute this. Let us suppose that x equal to u square. So dx will be 2u du, and adjust the limits. There is no change in the limits, and this gamma n becomes 0 to infinity. X becomes u square. So u to the power 2n minus 2 into u e to the power, in place of x we write u square. So e to the power minus u square into 2u du. Now adjust the power of u. It should be u to the power 2n minus 1 into e to the power minus u square du. Now let us take 2n minus 1 equal to 0, so that n equals to half. So gamma half should be equal to 2 into integral 0 to infinity e to the power minus u square du. Let us change the variable. Just write x in place of u. So it becomes 2 into integral 0 to infinity e to the power minus x squared dx, which gives you the result of this integral 0 to infinity e to the power minus x squared dx. It should be half into gamma half. Gamma half means root over pi. So the result is half into root over pi. Our time is over. There is just one more math. You can go through it by yourself. So I am closing the class now. I am closing the class now.
এই প্রুফগুলো কি মনে রাখতে হবে?
হ্যাঁ,
এই যে প্রুফগুলো করালেন এগুলো কি মনে রাখতে হবে?
Yes, you have to study this. এই প্রুফগুলো কিন্তু sorry, just a minute. হ্যাঁ, এই প্রুফগুলি you must memorize it. Sometimes
ওকে
হ্যাঁ, sometimes they are put in your exams, okay, in exam question. So I am leaving the class now. Thank you so much.
Ma'am, can you please upload today's slide and the previous class 1 improper integration 2?